Jai Hind to all. In this video, we will discuss the Ebers Moll model of the BJT, right. So, before starting with Ebers Moll model, first of all we will see the carrier distribution in the BJT, right. So, to start with, we will take the case of PNP transistor, right, and we are considering the transistor is in active mode. Okay. So, as we know, there are two junctions. So, this is junction, emitter junction, and this is collector junction, and we are considering the BJT is in active mode. So, this junction, emitter junction, will be in forward bias. So, here the width of depletion region will be very small, and this junction, that is collector junction, it is in reverse bias. So, obviously this should be the depletion region on this junction, right. Now, obviously this is your emitter, base and collector, and this is your PNP transistor. Okay. We are considering the concentration in emitter is Ne, the concentration of this base is Nb, and the carrier concentration of this collector is Nc. This the Ne, Nb and Nc, these are the majority carrier concentrations, right. Now, we have also taken this, that concentration in emitter side is greater than concentration of base, and this base concentration is higher than this Nc. So, we have taken highest doping in the emitter, then in base, and then in the collector. Okay. And obviously, we have also considered the transistor is operating in the active mode. Okay. Now, we can find the minority carrier concentration also. Okay. So, the minority carrier concentration, for example, in emitter is, we are considering it is Ne naught. So, Ne naught can be given as Ni square divided by the majority carrier concentration, that is Ne. Okay. Similarly, we can find for base, and base we are considering it is Pn naught, and it will be Ni square divided by Nb. Similarly, in collector it should be Nc naught, and it should be Ni square divided by Nc. So, as we have considered this Ne is greater than Nb and Nb is greater than Nc, so these concentration, these minority carrier concentration, should we can put them in reverse order. So, this Nc naught should be higher than Pn naught, and this Pn naught should be higher than this Ne naught. So, here we can take, this is your Ne naught, this is Ne naught, here we can take, this is your Pn naught, okay, and here we can take, this is your Nc naught. This will be the minority carrier concentration. Okay. Now, we also know that the emitter current can be given as, it is the summation of IEN plus IEP. Similarly, the collector current can be given as ICN plus ICP, and obviously the base current will be IE minus IC. So, what we will try to find out, before starting the Ebers Moll model, we will try to find out the expression of this IE and IC. So, for that we will find the value, or we will find the expression for IEP and IEN, similarly for ICP and ICN. Then we can write the final expression of these IE and IE current, and these equations will be very helpful when we discuss the Ebers Moll model. So, first of all we will try to find out the value of these. So, if we first we will take IEN. So, what will be IEN? IEN should be is equal to Q into A into Dn into del n by del x, and here we have considered this point is at minus xn, and because in this direction we are taking x, so here x is 0, here x is w, that is the width of this is w, base is w, and here this point is xc. Okay. So, with this assumption, this IEN we are calculating at x is equal to minus xn. So, what will be the value of this? This IEN will be is equal to Q into A into dN into NE naught divided by LE, which is the diffusion length in emitter, diffusion length of electrons in emitter, into e to the power VEB over VT minus 1. This will be the value of IEN. Okay. Similarly, we can find the value of IEP. IEP should be is equal to minus Q into A into dP into del P over del X at X is equal to 0. Right? Now, this del P of X can be given as, or this P of X can be given as Pn at 0 into 1 minus X upon W. Why we are taking this? Because if we see the magnetic carrier distribution in this, then the electrons are, because we have taken PNP transistor, the electrons are moving from N to P side, because this junction is in forward bias. So holes will move from P to N and electrons will move from N to P, and when electrons are moving from N to P, these electrons are becoming the magnetic carrier in the P side. So here we can say at this surface the electron concentration will be higher, and as we go deep into the P type, this concentration will reduce. Okay, so the profile will be like this. Similarly, if I talk at this point, what will be the magnetic carrier concentration in the base? So as we have taken base as N type, so for base, holes are the magnetic carriers, right? And holes are the majority carrier in the P side, and maximum holes are transferring to the base, right? So hole concentration will be higher here, and as we are going deep into the base, because we are taking base width is very low, base width is very low, so there will be very less recombination in this base region, and maximum holes will pass to the collector, right? So that means as we go deep into the base, this hole concentration will decrease linearly, and it will be 0 at X is equal to W, right? As we enter into the collector region, so this concentration, or this we can say electron concentration in this collector region, because it's a P type, it should increase like this. Okay, so here you can see in this base region, the magnetic carrier distribution is given by this linear line. Okay, so this condition we can justify with this equation. Okay, at X is equal to 0, if you put X is equal to 0 here, then the concentration will be higher. At X is equal to 0, the concentration is maximum, and if you put X is equal to W, if you put X is equal to W, then the concentration will be 0. Okay, so this equation is perfectly indicating that situation. So now this Pn naught, Pn at 0 can be given as Pn naught into e to the power VEB over VT, right? Now if I put this here, so P of X will be Pn naught e to the power VEB upon VT into 1 minus X upon W, and if I differentiate this, because I want to find out this del P over del X at X is equal to 0. Okay, so if I want to differentiate this, then I have to do del P of X divided by del X, and it will be is equal to Pn naught e to the power VEB over VT, and when I differentiate this, it will be minus 1 upon W. So this will be the value of this term. Now if I put the value here, the final value of IEP will be this minus will get plus, and it will be Q into A dP Pn naught upon W into e to the power VEB upon VT. This will be the value of IEP. So suppose we can say this is the equation number 1 and this is the equation number 2, right? Now we can find the value of ICP. ICP can be given as minus Q into A into dP into del P over del X at X is equal to W. At X is equal to W. And because IEP, that is emitter current, is approximately equal to the collector current. We have already considered base width is very narrow. It is very we have already taken it low. So this emitter current will be approximately equal to the collector current, right? So this IEP will be equal to the ICP. So same equation or same expression we can write here. So Q into A into dP into P n naught upon W into e to the power VEB upon VT. So this will be the value of ICP. And then we can find the value of ICN. It will be Q into A into DN into NC naught upon LC. This will be the value of ICN. This is nothing but the saturation current. Okay. So we can say this is equation number 3 and this one is equation number 4. Now what will be the total value of IE? Total value of IE will be IEN plus IEP. So we have from equation number 1 we have the value of IEN. From equation number 2 we can put the value of IEP here. So if I put the values, then we will get, so from equation 1, this is the equation number 1. So from here if I put the value, then IE will be is equal to Q into A into dN into NE naught, dN NE naught upon LE into e to the power VEB upon VT minus 1, right? This is from equation number 1, and equation number 2 is IEP is equal to, so here we can put Q into A into dP into Pn naught upon W into e to the power VEB upon VT, right? Now we can modify this equation. IE will be QA dN NE naught upon LE into e to the power VEB upon VT minus 1 plus Q into A into dP Pn naught upon W into e to the power VEB upon VT. If I add this term, because I want to make same here I have this exponential term as e to the power VEB upon VT minus 1. I want to make same here. So I will add this term and subtract this term. So Q into A into dP into Pn naught upon W and minus Q into A into dP into Pn naught upon W. So I will take these two terms and I will take common, and then IE will be Q into A into dN into NE naught upon LE into e to the power VEB upon VT minus 1, and if I take common it will be Q into A into dP into Pn naught upon W into e to the power VEB upon VT minus 1, right, plus QA dP Pn naught upon W. Now these two terms are common, so I can take them common. So IE will be, if I take them common, so it will be QA dN NE naught upon LE plus this term QA dP Pn naught upon W into e to the power VEB upon VT minus 1 plus QA dP Pn naught upon W. Now this term we can write it as IE naught. So the final value of IE will be, this IE will be is equal to IE naught into e to the power VEB upon VT minus 1 plus QA dP Pn naught upon W. This will be the final value of IE. Similarly, we can find the value of IC. So IC, we know IC is equal to ICP plus ICN. Okay, what will be the value of ICP? ICP is nothing but QA dP Pn naught upon W into e to the power VEB upon VT, right, plus value of this ICN is QA dN NC naught upon LE, oh sorry, LC. Now what I will do, sorry, QA dP Pn naught upon W VEB over VT, I will add this term and subtract this term. Why? Because I want to make same term here. Here I have this term VEB over VT minus 1. I want to make same term here. So VEB over VT. So I will add this term and subtract this term. So this will be QA dP Pn naught upon W minus QA dP Pn naught upon W, and last term is this one, that is QA dN NC naught upon LC. Okay, so I will take this term and I will take the common part out. So it will be QA dP Pn naught upon W. We can take this common, and inside it will be VEB over VT minus 1, right, and these two terms we can add. So it will be QA dP Pn naught upon W plus QA dN NC naught upon LC. This part is, we can say, this is nothing but IC naught. So the final value of IC will be is equal to QA dP Pn naught upon W into e to the power VEB upon VT minus 1 plus IC naught. This will be the final value of the collector current, right? Now from here we can also calculate the emitter injection efficiency, gamma. It will be IEP upon IEP plus IEN. We can find this. So I can modify this. I can write it as 1 upon 1 plus IEN upon IEP. We have calculated both values, so I put here 1 upon 1 plus, what is IEN? IEN is, where is the value? From equation 1 we can put the value. So it will be QA dN NE naught upon LE into e to the power VEB upon VT minus 1 divided by, what is IEP? It is QA dP naught upon W into e to the power VEB upon VT, right? So if I consider this VEB is too small, so these values will be almost equal. So we can neglect, or we can cancel out these terms, and this QA will be cancelled out by this. So what will be the final value? We can write it as 1 upon 1 plus dN into NE naught, dN into NE naught into W divided by dP into P n naught into L. So we have found this expression. Now again we can modify this. This gamma star will be, we can write 1 upon 1 plus dn into this NE naught. NE naught we know, NE naught is nothing but Ni square divided by Ne. So we can write this. So here I can write Ni square divided by Ne into W, and similarly here I have dP into Ni square divided by, what is this, P n naught. So here I can write Nb into Le. Okay. Now this gamma star will be 1 upon 1 plus dn into Nb into W divided by dP into Ne into Le. So this will be the final value of emitter injection efficiency. From here we can see, if we try to keep this near about to 1, then this Nb over Ne, what should be this? Nb over Ne, it should be as small as possible. That's why we keep Nb less than Ne. And similarly here, if we see this W by L ratio, this Le is the, we can say, diffusion length of electrons in emitter region. So we can say this is the width of emitter, okay, emitter width, and this is the width of base. So this W by L ratio should be less than 1 if we want to keep it 1 or make it 1. So this W by L should be less than 1, and how it is possible? If we make the emitter larger as compared to the base, or if we keep the base as small as possible. So this is the reason why we make the high doping in the emitter region and why we keep base region as small as possible. Okay. Now come to our main topic, Ebers Moll model. Ebers Moll model. In Ebers Moll model, what we do, we will try to make a BJT from the two back-to-back connected diodes, right? So we will try, if I connect a diode here and a diode here, so it should behave like a transistor. It should behave like a transistor, because in transistor we have taken the example of PNP. What is happening? So this is suppose P region or P positive region, this is N region, again this is P region. So there is one junction, this is junction JE, and second junction, this is junction JC. So there are two junctions between P and N and P. So we can consider here, we can connect the two diodes, because this junction is in forward bias. So we have connect diode like this in forward direction, and here this junction JC is in reverse bias. So we have connected diode in the reverse direction. Okay. So this arrangement should behave like the transistor, but here we will also consider, because these two junctions are, we can say, depending on each other. Okay. If we change the value or voltage across this junction, then the current across this junction will change, and if we change the value of voltage of this junction, then the current through this junction will change. So these two junctions are depending on each other, but here these two diodes are not depending. So we have to change this, and we will add one more term here, and that will be for example, if IF current is flowing here and IR current is flowing in this direction, then this factor will be alpha R into IR, and this factor will be alpha F into IF. So these two factors will have to taken, so that these two junctions or these two diodes, we have to make them interactive. Okay. Now what will be the value of the current IE, IB and IC? What should be the value of these current? So first of all, write the value of IE. From this figure we can see IE should be is equal to IE should be is equal to IF minus alpha R IR. IF minus alpha R IR. And IF is the forward current. So I can write IE will be is equal to IE naught into e to the power VEB upon VT minus 1 minus alpha R into IR is the current from this diode, it is flowing through this diode. So it will be IC naught into e to the power VCB upon VT minus 1. So this will be the value of the emitter current. Okay. Now if we talk about the collector current IC, what should be IC? IC, it should be is equal to alpha F IF minus IR. Alpha F IF minus IR. Okay. So here if I put the value of IF, it will be IE naught into e to the power VEB over VT minus 1 and minus alpha, it should be IR. Value of IR is IC naught into e to the power VCB over VT minus 1. So this should be the value of IC. And what should be IB? IB should be from here, if I write, IB will be IF plus IR minus alpha IR minus alpha IF. So IB will be IF plus IR minus alpha F IF minus alpha R IR, right. So if I take these two terms, that is IF and alpha R IR, so it will be IF minus alpha R IR. So one term is this, and if I take minus common, so I can write alpha F IF minus IR. So this is nothing but IE and this is IC. So this will be the value of IB. Now this model is the large signal model. This model is the large signal model, and these equations that we have derived, these are applicable for all the modes. That is, these equations of emitter current, this is the equation of emitter current and this is the equation of collector current. These equations are valid for active mode, cutoff mode and saturation mode. Okay. So now if I write these equations for active mode, these equations will be, I can modify this, IE will be equal to IE naught into e to the power VEB upon VT minus 1, and in reverse bias, as the saturation current will be negative, so I can write it as minus will be plus alpha R into IC naught, right. And then I can write the current IC. IC will be alpha F into IE naught into e to the power VEB upon VT minus 1, and it will be plus IC naught, okay. Now suppose this is equation number 1, this is equation number 2. Now we have to compare these equations, what we have derived here, this. So IE we will compare with this, okay, and then IC equation or equation number 2 we will compare with this equation, right. So if I write these equations here, so these are previously obtained. So IE we have obtained as IE naught into e to the power VEB over VT minus 1 plus QA dP Pn naught upon W, and similarly IC we have obtained as, IC was Q into A into dP P n naught upon W into e to the power VEB upon VT minus 1 plus I C naught. And if we compare these equations, compare 1 with 3 and 2 with 4. So what you will get? You will get alpha R into I C naught equal to this, right? And alpha F I E naught will be equal to this. So I can write this. So alpha R I C naught will be is equal to QA dP P n naught upon W, and similarly alpha F into I E naught is equal to QA dP P n naught upon W, and these two terms are equal. So I can write alpha R into I C naught is equal to alpha F into I E naught, and I can consider this is equal to IS. So now I can find out I C naught. I C naught will be IS upon alpha R, and I E naught is equal to IS upon alpha F. And now these values I can put here. These values I can put here in this equation. So if you put these and write the final equation of the emitter current and the collector current. So this is the Ebers Moll model, and we have checked or we have write these equations for the active region or active mode. Okay. So this is the way we can perform the Ebers Moll, or we can analyze the Ebers Moll model.